Good afternoon. Today we are going to discuss regarding authentication and key generation in IEEE 802.11i. So basically today's topic is this, where how exactly we are going to perform authentication and how exactly we are generating the keys for exchanging the information that we are going to discuss today. So before going for this discussion, just I wanted to highlight the things that what we have discussed. So that is authentication in WEP, wired equivalent privacy. Okay, so in the last class I told you regarding say the station and the APs, how exactly they authenticate with each other. Okay, so here we are not taking a support of any third party, and basically a station which wants to authenticate itself to a AP, yes, or AP whenever it wants to say identify the station, say it is based on challenge response technique. So basically in wired equivalent privacy technique, so the challenge response protocol is used, which is not that secured. So in this case what happens, say basically a challenge will going to be generated by AP, that is a kind of a nonce which is going to be sent by AP to our stations. Then stations using this challenge and a kind of a key stream which is used as a function over here with the input that shared secret and identity vector, and the outcome of this will going to be say XORed with a challenge, and that we call it as response. This will going to call it as a response. This response will going to be sent back to the AP for authentication purpose. The major drawback, as it was told to you in the last class, that it is very easily we can this particular algorithm will be subjected to replay attacks. Basically dictionary attacks, say the different types of attacks to which it is vulnerable is dictionary attacks and say replay attacks. And since there is no proper authentication involved, it is also opens the doors for man in middle attack. Now we are going to discuss regarding say the authentication process that is used in a IEEE 802.11i. Okay, so basically in this process we are talking of using some third party for authentication. So actually here only access points and our stations are not involved. We also need a support of some third entity, that is server. We need some authentication server in this whole activity. So in our discussion I am going to use a radius server for authentication purpose. So as you know the jobs of AP and the station, in say in this process we are calling AP as supplicant, stations as a supplicant. These are our stations. We identify station as a supplicant. We identify access points as an authenticator. So these are our authenticator, and the third entity is our authentication server. That is a radius server in our discussion. Okay, basically this authentication happens in IEEE 802.11i with the help of extensible authentication protocol. Actually, it is not a single protocol. It is a group of a protocol. Actually, it is a kind of a framework through which the authentication happens. Okay. So, how exactly EAP works, and we will going to discuss different versions of EAP. So, basically, here we are concentrating on two versions of EAP, that is Eap Md5. So, which is very simple among the set of EAPs that are provided. So, the second we are going to discuss regarding Eap TLS. Yes, so which is very much secured among the list of EAPs. So, the higher version of it is Eap TTLS. So, these are a few. Apart from this, say few more are there, but we will concentrate our discussion only for these two. Fine. So we'll see to it how exactly the authentication process happens. I'll talk regarding some certain generic messages that are going to be exchanged between different entities. Just now I have told. So how exactly the authentication process takes place. Okay. So to know regarding that, I'll talk regarding a figure through which I'll try to explain the process of authentication, which involves authentication server. This is my server, authentication server. So this is my access point, and this is our stations. Station I am identifying using the letter S. Say this is our access point, and this is our authentication server. So as you know that here I will start this discussion with the assumption that APs and say stations, they have already associated with each other, as you know. Okay, so association of AP and the station involves exchange of some frames between them. So the few frames that are getting exchanged between the access point and the station, I told you in the last class. So the frames that are generated by AP are, say, beacon frame. Yes, and the second frame that gets generated by the AP is response frame. Yes, so this particular response frame is in reply to a request frame that is generated by station. Rather than calling simply a response frame, I'll just call it as probe response frame. Probe response frame. So these are the two frames that will move from the access point. So this is a reply to the request that is generated by the station. This particular frame, it is actually a reply. It is a kind of a reply that is generated by the say the request that is generated by the station. So this beacon frame is generated by AP on its own. Okay, so these two are the things that are originating from AP, but this is in response to the request that is made by the station, whereas beacon frame is generated on its own. Okay, the second frame, say when it comes to the station deals with probe request frame. So in response to this request, response frame will going to be generated. Now in this case, whenever a probe request frame gets generated, normally, as it was told to you in the last class, that request and response frame and a beacon frames are meant for associating AP with the station. So whenever some station enters some wireless network area, so what it will do is to get associate itself with some particular AP, it first sends its request, or sometimes APs, they themselves try to probe who all are there in their area. So in that situation, AP propagates beacon frame to identify newer devices which are in its range, or otherwise stations on their own, they propagate request frames. On their own, they propagate these request frames to identify the APs. So it depends on the situation. Fine. So in response to this request frame, EPs will reply with response frames. Okay. Whereas beacon frames are generated on its own by AP. Now, these particular frames contain some of the, say, cyber capabilities of those devices. Especially when it comes to a AP, it announces its capabilities either through response frame or through beacon frame to the receiver. Whereas when it comes to the station, it announces its capabilities. Here, the capabilities in the sense the cyber capabilities, okay, to the other party with the help of request frame. So these are the one which are helping these two stations to associate themselves with each other and also announce certain information regarding them. So actually these two are the one which are helping them to associate with each other. So association does not mean that they are allowed to communicate. So association is the first step. After that, they will going to authenticate each other. So in an older version of IEEE 802.I protocols, the association used to happen after authentication. But in the newer version, association happens first, then the authentication takes place. So slightly a modified one. Okay. So now how exactly the authentication and association happens, that we are going to see. So to start with, APs. Okay. So APs will going to send a request to the stations saying that it is identity request. You can say call it as ID request. Yes. So AP is the one, here we are assuming that AP is the one who is initiating the communication. ID request will going to be sent by AP. For that, ID response will going to be generated by the stations. So once this gets received by the AP, yes, AP say sends an access request to the servers. So you can call it as radius access request. Okay. So since I am talking regarding, say I am assuming this authentication server is a radius server. So with that assumption, I am saying that it's a radius access request, or otherwise simply you can call it as access request is going to be forwarded by AP to an authentication server. So for that, it will give access challenge. It gives the access challenge. It gives the access challenge to a, say, passes the access challenge to a AP. So once access challenge comes to a AP, what AP will do is it will ask the sender, I mean station, for authentication request. Authentication request message will going to be generated by AP, because it is posing the access challenge. Based on this challenge, it is probing the station for authentication purpose. Now the actual authentication starts here. So for that, it will reply with authentication response. Yes. Once it gets an authentication response for the request what it has made, then what it will do is it will forward that message to a authentication server. Now forwarding of that message does not mean that it is going to forward it directly. So again, it is kind of a access request. It's kind of a access request. So same as this, and for that, say access granted reply. Okay, so otherwise you can say access accept. So it grants the access to the AP. So this is how the whole, say, accept request. So this will going to be forwarded back to it saying that success. So once it gets successful, the whole authentication process gets over. So that means from this whole discussion, one thing is very clear, that the access point is acting like a mediator of exchanging the messages. Basically, it is the one which is posing the access request. This is the one which is sending the say that challenge to the stations. Stations are say replying back to the challenge. Based on that reply, the server will going to confirm whether it is allowed to access the services or not. So this is how the authentication server works. Okay. Now basically what exactly happens in this authentication steps, okay, that we need to see. So just now I told you like what are the different types of messages. They are very generic. They are not specific to any particular say extensible authentication protocol. Okay, so they are general messages which are exchanged between authentication server and access points and stations. Okay, now we will try based on say specific protocol, we will going to rename those messages. Okay, so when it comes to Eap Md5, as I said, I am going to discuss only regarding two protocols. So that is Eap Md5. As you know, it is a message digest 5 protocol, extensible authentication protocol. So which is a message digest, as a name suggests, message digest 5. So basically here the request from the authentication server, okay, so that is your radius server, basically it is requesting the stations to send its reply or send its password. Reply here indicates basically it is what, it is a very simple protocol. As I said, it is simply asking stations, see, this request is not directly going from the server to the station, it is going through a AP. Okay, for understanding reason I am just showing it over here, saying that server challenge is what, it is asking it to send its username in encrypted form to it. Okay, so actually it is asking it to send the hashed output of the username with the help of the pre-agreed algorithm. So it replies that back with the MD5 algorithm, so generating the hashed output of that input, and using this MD5 algorithm, then it sends that to a server. So moment server gets it, it verify its integrity, whether it is a true station or not. So anyway, server 2 knows regarding this algorithm, how exactly it operates. It knows what are the keys that are supposed to be used for this algorithm is known to the server. So based on that, verification of the encrypted that hashed output of username will go to be verified at a server. Integrity check takes place. Based on that, server will conclude whether it is allowed to access the services or not. So this is how the MD5 works. The second version of this is the TLS. Basically, the original version of TLS where Eap TLS, where it mandates both for server as well as AP as well as stations to have a certificate, that is digital certificate through which they should communicate. This is what it mandates. Assigning the certificates to an AP is acceptable, but you are allowing the stations to join a AP and leave a AP, and providing PKI support, say your public key infrastructure support to a stations is a bit difficult task. So APs we can provide, but whereas providing a support to a stations is difficult. So this is bit tedious job. So it will not going to work out in a smaller say organizations and all. For their purpose, EAP slightly modified. We call that as tunneled TLS. So I was talking regarding the tunneled TLS method, where a station AP access point, say one which is say working with digital certificate, authenticates itself with the stations. It performs the authentication task here first. So it starts an authentication. So once it starts the authentication by authenticating itself with the known keys and all, so then they start agree upon some secured tunnel. So with the help of the things supplied by the AP, both of them agreed to create some secured tunnel through which they will exchange their messages. Once a secured tunnel exists between AP and a station, then AP and station, the station first authenticates itself to the AP. So once authentication of station gets completed through this secure channel, since station does not have that say way of communicating or authenticating itself in a secured manner to the AP in TLS, so internal method is used. So in say here, as it was told that it does not need to have a certificate, only this is having a facility of getting a digital certificate, digital signatures. So because of that, it can authenticate itself to the stations. So once it authenticates, then these two agree. In this authentication method itself, AP conveys that to a S to go for secured tunnel. So once they agree, they create a secured tunnel through which station authenticates itself to a AP. So once this authentication gets over, then the further communication takes place between stations and a AP. So this is how EAP TLS works. So this is regarding authentication in IEEE 802.11i. Now we'll talk regarding key generation. I will talk regarding a key generation or key hierarchies that is used in say IEEE 802.11i. Okay, so basically here we are talking of say generating pairwise transient key PTK, which is of 384 bits long. So generation of this pairwise transient key is main goal in key generation. So this will going to be generated with the help of pairwise master key. Okay, this gets generated with the help of PMK. So pairwise transient key is of 384 bits. This is of 256 bits. Okay, so this PMK in turn, see, it is not an agreed thing. Actually, this PMK is helping us to derive the PTK, but this how exactly the PMK comes here? The PMK comes from either of the two ways. Okay, we have pre-shared session key, PSK, pre-shared session key. This is previously shared. It is an agreed key. Okay, PSK. With the help of this PSK, they derive PMK. This is one possibility. This is one way of getting the PMK. Otherwise, say master session key, MSK. Okay, master session key or PSK. So when it comes to the master session key, this particular key is exchanged during the authentication time. So previously what all the authentication processes we discussed, during that time this key was exchanged between the APs and the stations. So with the help of this they derive PMK. This is one way of deriving the PMK. The second method of deriving the PMK is PSK. Either of these method will going to be used for obtaining the PMK. Once a pairwise master key is generated, then the PTK will going to be generated with the help of this PMK. So using this PTK, basically it is a transient key. So because it will not going to be used, this particular PTK will be used only for one communication. Thereafter, for every new sessions, new PTKs will going to be generated. So this PTK helping us to generate three different keys. One is a temporal key. See, all of them are 128 bits. These three keys are of 128 bits. So second is KCK. Okay. Third one is KEK, key encryption key. Okay, so these are the three keys which will going to be obtained with the help of PTK. Now basically what exactly these things will going to help us to do? So basically these are the keys which will going to be used for the further say communication. Now authentication is done between AP and the station. Authentication itself will not going to be used for further communication. Say further communication that is happening between stations and AP, that has to happen in a secured manner. For that purpose we need a support of these keys. Okay, so these three keys will be used for secured communication. So as I said, we will be talking regarding three keys, that is temporal key, KCK and KEK. TP, KCK and KEK. So basically in these three cases, temporal key or your KCK and KEK. So basically here in this case 128-bit keys, these are all 128-bit keys, and before going for say how exactly these keys will going to be generated, in what method these keys will going to be generated, to know regarding that, before going to that I just wanted to add one more information, that is say the keys, the two different types of keys what we use in communication between AP and the station are either it is pairwise secret key, or it is a group key, group secret key. So because when it comes to a communication in wireless LANs, say that is happening between AP and the station, either it is a pairwise, either it is between AP and a station, a single station, or it may be a say multicasting type of a communication, or say it may be of the type broadcast type of a communication. So out of these, say based on what type of communication the AP and the stations are doing, based on that we are talking of using these keys. But right now what I am discussing, though that particular discussion is either it is generating a pairwise key, basically it is generating keys which will be helping us for communication or when it comes to exchanging of these keys between AP and the stations is done with the help of those keys what we are generating now. Okay, so we will talk regarding those keys generation. So these keys will going to be generated with the help of four-way handshake method. So we talk regarding four signals that going to be exchanged between your AP and a station. So basically to start with, so here AP generates a nonce. Yes, so I am going to call that as NA. The nonce which is generated by AP, I am going to call it as NA. So in the second message, so we are talking of generation of second message which involves NB, that is again the nonce that is generated by station. So either you take it as, say since station I will just use it as NS. Okay, so nonce that is generated by station, and say the cipher suit which is supposed to be used between them, and MIC. So it is basically message integrity check. MIC here indicates message integrity check. So this will going to move from station to a AP. Now see, basically when it comes to a second message, I said that it will going to generate NS, a cipher suit which is supposed to be say going to be used by this station, and MIC. So message integrity check information which is generated by station. Now this MIC, message integrity check, will going to be generated with the help of KCK. Now the KCK comes into the picture. Now I said these are the things how they have to be generated. As I said, PTK is generated with the help of PMK as it was told. So this is obtained with the help of pseudo random function PRF. I am just writing it as PRF, pseudo random function. So this pseudo random function helping us to generate this PTK from PMK. So PMK is pairwise master key. Yes. So that PMK is one is which is helping us to generate this PTK. Yes. So PTK is giving a birth to KCK. So first we are talking regarding generation of PMK, that is obtained with the help of some shared master key or master session key or shared key. Either of the either by using either of the techniques we are generating this PTK. So then the PTK generation is done with the help of PMK and with the help of NS and NA. See, moment it conveys the nouns, okay, some random number, when it passes it to a S using that NA, that random number which is generated by AP, so that's why I am calling it as a NA, and this NS which is going to be generated by the station, so that is, it is already known regarding that random number, so it uses it. Then say MAC IDs of both, MAC addresses of both station as well as AP. So you know that MAC address is of 48-bit length. So those informations along with these nonces and PMK will be used to generate the PTK. This is how the PTK will going to be generated. So pairwise transient key will going to be generated. So this in turn helps us to derive the KCK, KEK and TK. Okay. So once KCK gets generated, with the help of that KCK, they will go to generate this message. It is kind of a signature kind of a thing, or some hashed output which will go to be generated with the help of the message that what we have generated. So this is hashed output is generated with the help of this key. Along with that, we are generating NS and cipher. We are also sending a cipher suit to a AP. Now, see, already there those keys are getting generated at a station, and what is the nouns that is used by the station, it is forwarding it to AP, and to identify the integrity of these things, MIC has been forwarded along with these information. Now see, it does not need a encryption of these things, because MIC itself will going to give whether these things, whenever it receives, it verifies these things with the help of MIC. Okay, moment it gets NS over here, it also generates those keys, that KCK, KEK and say temporal key, TK. All these things will going to be generated at receiving sides 2 also. So then what receiver will do is, say it passes the information back to a station. Okay, so in this case it will send GTK, which is group wise transient key, GTK. Basically this is, as I said, it is meant for helping say AP and the stations to communicate in a say broadcast manner. Okay, so basically it contains a broadcast keys, then cipher suit, then it will also generate MIC to confirm itself that it is a AP to a station. Yes, so it also generates MIC using same KCK that is generated at its side. Okay, the KCK what is getting generated over here and what was the KCK that is generated over here, both are same. So using that KCK, it conveys the message back to a server saying that okay, this is the information I am passing to you. So once it passes all this information to this, so the authentication part of the authentication gets over. Okay, then it acknowledges the whole thing with the help of, see, one more thing, last thing here, it encrypts all this thing using KEK, key encryption key. Basically it encrypts all these things using KEK because it is propagating GTK here. It is propagating GTK. It is no need to encrypt this part. So basically this encryption is done basically for this purpose. Okay, GTK is also sent along with this information. So it is not supposed to be known to other parties or known to the say some rogue machines. For that, to protect this GTK from say unwanted users, this will going to be encrypted with the help of KEK. Then whole thing will going to be confirmed. Okay, so then to say that authentication is successful, it sends an acknowledgement saying that okay, message authentication confirmation, your MIC will going to be sent. Fine. So with the help of this, these two confirms themselves both of them authenticate, both of them agreed upon the key, and further communication between stations and AP will happen through with the help of those keys which were generated. So here temporal key will going to be used for exchanging of messages. So this is how the four-way handshake helps both the stations, both station as well as AP to generate the required keys and communicate in a secure manner. So this is regarding key generation. So this is how IEEE 802.11i authentication as well as key generation activity takes place. So it needs a support of, for all these things to carry out all these process, it also needs a support of radius server. Authentication basically happens here with the help of radius servers or some third party server, and then the secured communication takes place between AP and the stations with the help of the keys that right now they have generated. Next, we will going to discuss regarding, say, basically the modifications that are done in wired equivalent privacy techniques. So how exactly these modifications helps us to access the net with the help of in a secured manner. In this category, we are going to talk regarding wired protected access 1, WPA1, WPA2. Today I am going to discuss only regarding WPA1. I will leave WPA2 for you people. So basically how wired encryption process is made secure with the help of some modifications that is addressed in WPA1. So it is also known as TKIP technique. Okay, so basically this too also adopts, as you know, that RC4 technique. So pseudo random key usage of this RC4 technique, which was not that secured, which was already discussed in the previous video, where we were talking of calculating, say, response with the help of challenge, and that challenge get challenge which was getting XORed with key stream function, and it was generating the response. This was the technique which we used. We know that this was not that secured for communicating in a wireless environment, because even though we are talking of using a RC4 technique, so it has too many vulnerabilities where any hacker or anybody can, say, get this information with the help of dictionary attacks or man in middle attacks. Okay, so to overcome those vulnerabilities, we are talking regarding two different techniques. So that is our WPA1 technique and WPA wireless protected access 2. Okay, so I will start our discussion with the help of, say, TKIP, data protection using TKIP. What exactly happens in the TKIP, that I will just highlight you how exactly the WPA1 makes the secure communication, or the keys will go to be, how exactly the keys will go to be generated in that RC4 will go to be generated in WPA1. So that I am going to discuss in this part. So basically here we are talking of using two functions, two pseudo random functions. So PRF1, PRF2. So these two in turn will help us to generate the required key that is needed for communication. Okay, so PRF1 function basically generates a 80-bit output. So this 80-bit output will going to be obtained by, say, temporal key. We need some temporal key TK, so which will going to be used. So then MAC address of sender, which is of 48 bits long. Yes, so then we talk of usage of, say, sequence number. Basically this is a sequence number count that is used for, say, counting the number of frames that are moving between sending and receiving. So sequence number count, a sequence number you can say. So here all 48-bit sequence number count will not be used. Actually this sequence number count length is 48 bits. Out of this 48 bits, MSB32 bits will going to be used. MSB32 bits will going to be used. These are the inputs to this pseudo random function 1. So this generates, as it was told to you, it generates 80-bit output. So this will be one input to say your PRF2, and remaining 16 bits of this 48 bits will be used as another input to this. These 16 bit and these 80 bits together will going to generate say 120 bit output. 104 bit output. So this 104 bit output will going to be a part of our key RC4 frame key. So 104 bits, and remaining 24 bits will going to be obtained from sequence number. So this sequence number 24 bits and these 104 bits altogether, it is 128 bits. These 128 bit key will be used in a modified say wired equivalent policy for protecting the data that is going to be exchanged between sender and a receiver. So this is how they made WEP stronger with the help of this technique. Again, it has a few flaws. So these flaws are overcome in WPA2. Okay, wireless protected access 2. Okay, so in WPA2 they try to overcome most of the drawbacks of this. Okay, so this is regarding